All right, this is how to do a projectile problem. Well, in a typical projectile problem, you're going to have some vector, some magnitude, in this case 500 meters per second, at some angle above the horizon. And there are two questions that can be asked, and the typical one is, how far? How far? In other words, when you shoot this, how far away will this land? There's one other question that can be asked. How high? So how high is it going to go when shot like this? So in all of these, we have to remember, what does a free body diagram of the object look like? All right, once it's been shot, what's the free body diagram of the object as a projectile look like? Are there any horizontal forces? Well, if it's shot at a high velocity, there certainly is going to be air friction working against its velocity. High school physics, though, we tend to ignore air friction a great deal, and truth be told, it's very often not a really big force unless you're at a very high velocity. So we're going to be ignoring the air friction. There's certainly no up force, so the only force we have that we're going to be working with is the object's weight. That means, just like in the cliff problem, we're going to have to break it up into a vertical velocity and a horizontal velocity. So in order to do this, we have to take the triangle and calculate your vertical velocity and also calculate your horizontal velocity. For that, we need some simple trigonometry. So, well, we know the sine of 30 degrees is 0.5. So over here, you're going to be rising at 250 meters per second. And 30 cosine is that 0.866 thing. So multiply that by 500. And so we have 433 meters per second going in the horizontal direction, 250 meters per second going in the vertical direction. Well, before we start this, why don't we come up with a quick estimate of how far away it's going to land? That'll guide our thinking here. So, if you're rising at 250 meters per second, how many seconds is it going to take you to get to the top of that? Now, if you've been working with me, you just said 25 seconds. If you haven't been working with me as much and you're slow on that, think about this. Acceleration due to gravity reduces your upward velocity by 10 meters per second every single second. It'll add to your downward velocity by 10 meters per second every single second. That's what acceleration due to gravity is. So 1 second after it's launched, it started at 250 meters per second. 1 second after that, what's it going to be? 240 meters per second. Another second later, it'll be 230. So, yeah, it'll take 25 seconds to reach the top. After it reaches the top, how long before it reaches the bottom? Another 25 seconds. So we know here that it's going to be about 50 seconds, top and bottom. Well, for that entire 50 seconds, every second, it's moving 433 meters per second. So if you just go 50 times 433, you have 21,650. I'm going to store that. All right? That's how far we're saying ballpark without us doing any actual calculations. That's about how far away it's going to land. Huh. Can we also use super simple methods to figure out how high it's going to go? Well, think about this. If it starts at 250, it ends at 0 when it's as high as it's going to get. What's its average velocity? Right? Well, its average velocity would be 125. You get that? Sort of like a drop problem in reverse. So it's averaging 125 meters per second. How many seconds till it comes to a halt? 25. So take its average velocity times 25. So we know it's going to climb about 3.1 kilometers high, and it's going to go about 22 kilometers far. So without doing any real work other than just solving the triangle and knowing some basic physics, we already got good answers here, so we can check our work. If we don't get those answers, we better check our work a little bit more carefully. So to do how far? The first set of givens are going to determine how long it's going to be in the air. So they're going to be the vertical givens, the up and down. Now, key to understand, initial velocity. You must never use this number. This number, once you have calculated this stuff, that number never belongs because it's a combination of two vectors. There's acceleration in the up and down direction. There's none in the horizontal direction. So that is useless other than filling out our triangles. So our VI is 250 meters per second. Well, what is its velocity going to be when it gets back to the ground? And I don't mean after it's landed. Think about catching it. What's its velocity going to be when it gets back to the ground? It's going to be this, but negative. So it's going to be negative 250 meters per second. These things are symmetric. All right, the acceleration we know is going to be due to gravity. And in this case, because we have a positive and a negative, we also have to be very clear that the acceleration is negative. The acceleration is in the downward direction. And we want to know the time. So the formula, we're back at a nice simple formula. Acceleration equals the change in velocity. And change in velocity is VF minus VI over t. So to solve, t equals VF minus VI over A, S and S. T equals VF minus VI over A equals negative 250 meters per second minus 250 meters per second, all divided by negative 9.8 meters per second squared. So we know it's going to be about 50 seconds. So let's see what we get here. 250, make it negative, minus 250 equals minus 500, we knew that, divided by 9.8, and that's negative. That all equals 51.0 seconds. Is that in line with what we were thinking? It certainly is. So now we have the givens horizontal. And what are they? Well, the velocity. And this is just velocity. There's no change in that velocity, no acceleration in it, so it's just 433 meters per second, and we just call that a velocity. The time, 51.0 seconds. We're looking for the distance. The formula here, this is a non-accelerated direction, so velocity is distance over time. Distance equals, multiply both sides by time. Distance is velocity times time. And our S and S, 433 meters per second times 51 seconds. Those seconds cancel out nicely. And I'm using the whole number, not just the 51, times 433. And that equals 22,091, which is right in line with what we were thinking. So what can I say about that? I can say 22.1 kilometers. I could also say, if we look at where the decimal point is, and I want to move that over for scientific notation, well, if you look at your calculator, right above the number 5, it says SCI. If I press scientific notation, it'll do it immediately for me. And it'll give me 2.2, and if I'm rounding that, and my calculator will do that too. Second fix 1, or second fix 2. All right, so I could fix the decimal places there. This I can round to 3 places, so 2.21 times 10 to the 4th meters. That would work great. Now, if we want to figure out how high, how do we do that? Well, for how high, it's only going to be using that. All right, so we're just going to take our givens, And we can say vertical, but everything we do is vertical, so we don't necessarily have to break that down. The velocity initial is 250 meters per second. Now, what's the velocity going to be when it gets as high as it's going to go? Right, so the final velocity is 0 meters per second. Notice here, you needed to have it get all the way back to the ground because it's moving forward that entire time. Here, you just want to get it to the highest part of its trajectory. So that's when its velocity vertical goes to 0 meters per second. Acceleration is gravity. We're all in one direction here, so don't really have to even worry about the negatives now. And we're looking for the distance. All right, and I'm going to make the gravity negative anyway, just because I think that's going to be important. Formula. What formula? Well, how about we look in, and what is a formula that relates to these? And after you fuss for a little bit, you'll find VF squared equals VI squared plus 2AD. Okay, so we're solving this for D. So VF squared minus VI squared equals 2AD. So just divide the 2A over, and that leaves you D. So what do we have? Well, VF is 0, so we have a negative 250 meters per second quantity squared divided by 2 times negative 9.8 meters per second squared. Right, so we see the negatives are going to cancel out here. Happy days. So we can just do this. 250, don't forget to square it. X squared divided by 2 divided by 9.8 equals, all right, 3,189. Well, look at that. It squares up nicely with us here, and so that would be 3.2 kilometers, or if I put it in scientific notation, 3.19 times 10 to the third meters would be how high. That's how far. And that is how you do projectile problems, right? Equals 3,189 meters. And that I put up there because I don't have the right to all of that. All right? That's how you do it. I hope it works out for you. Enjoy.